Hi everyone and welcome back. I am Miguel Alfonso Mendez and I'm welcoming you here to the last video of the course dedicated to the theoretical background of SPICY. Now so far we have talked about the general idea of using RBF approximations for regression and for solving PDEs. Then we talked about how to introduce penalties and constraints, and in the last two videos we saw how to use this framework for solving a velocity regression problem and pressure computation in incompressible flows. There were several things I did not tell you about, which I would like to group here now under the umbrella of numerical methods, and this will be the last topic that we cover with this video. Now, I divided the video into two parts. The first part is dedicated to clustering, and this is what we use to define the shape and the collocation of our radial basis functions. You might recall from the first video that our business here is to try to approximate a function using a linear combination of functions which are our bases, our radial bases. Now, these bases are defined by a collocation that sets where these bases will be located and a shape factor that tells us how large or small this basis is. And for the entire course up to now, I've been telling you, forget about the collocation and the shape factor, imagine that these are given to you, and up to this moment we are only focusing on the weight vectors. Of course we like this because the problem is linear with respect to the weight vectors. But how do we get this collocation and shape factor in SPICY? Well, the first idea that comes in mind would be to just include these parameters in the cost function that drives the optimization, let's say, that is used to train the regression. So here, for instance, if you are, I'm recalling what could look like if we deal with a regression problem, where our cost function is the L2 norm of the error of our approximation, and we could make this depend on the collocation and the shape factors. Now this brings many problems. The first is of course that this becomes nonlinear and much larger, because if you look for instance the problem in 3D, you will need one collocation requires 3 coordinates plus the shape, so you need 4 extra number for each radial basis function, and the problem is already big enough and you're going to multiply it by 4 by 4, so by 16. And the other problem is that, as I said, is non-linear. We might not be too much scared about this if you consider that this cost function is analytical, and we can very easily differentiate it and compute the gradient of the cost function with respect to the parameters that we are talking about. So in this case I'm showing you, for instance, the gradient with respect to the shape factors, and once we have the analytical gradient we can use very powerful gradient based methods to solve this problem. Now the truth is that this is very difficult. We spend an horrendous amount of time playing with this, and I will not recommend to walk along that path. Most importantly because we think that, at least for the problems that we have seen, it's not really worth it. Now what do I mean by that is that we have noticed that by playing a lot with the code that in general the optimization was successful when it was placing the RBFs in such a way that it had more or less an equal number of particles or integration points under each of the RBFs. Of course we have no mathematical proof to say that this has to be the case and that this is the normal way things should go, but that's just an intuition, just a fact that we have noticed. And so we decided to bypass the optimization, and we came out with an idea that tries to implement the same principle but in a much faster and easier way. And that took us to the idea of a clustering algorithm, in particular a hierarchical clustering approach. So here I want to show you the algorithm. The starting point, as you can expect is that you have some particles or some integration points. Say you have NP of this, and then you want to define the number of bases that you will place. But in SPICY you define this indirectly. It's very hard for you to know how many of these you have to put. But what you can estimate, and that with experience you will learn how to do that quite easily, is what is a good number of particles that should be under 1 RBF. And we call this number here NK1. The reason why I put a 1 will become clear very soon. So here in our example, say I have 30 particles and I say NK5. What I'm saying is that I just want to have 6 RBFs. And what do we do with this? We use a clustering approach, and we do that using the k-means clustering algorithm, which is a very popular algorithm in machine learning. If you have never heard about it, I encourage you to look for it, and you will find a lot of material out there about this. Now what this algorithm does, it solves also an optimization problem, and tries to regroup these particles based on similarity, and in this case similarity means distance, Euclidean distance in our problem. And so it will try to look for the set of barycenters. In this case 6, k is the number of clusters, that's why we use the same notation, in this case 6. And these clusters should be placed in such a way that their barycenter minimize the distance between particles within the same cluster and maximize the distance between particles in different clusters. So let's say that the result is something like that. I'm putting in red the barycenters. The next step will be to connect these barycenters. They will be used as collocation points, and the size of the bases will be based on the value that each RBF will have at its nearest centroid, at its nearest barycenter. Okay, and the value that defines this is what we call here the epsilon. So let's say that I say, for instance, that epsilon has to be 0.5, then say this RBF has to have a radius equal to a value equal to 0.5 at its nearest neighborhood, and from there you can then compute what is the shape factor, because you find a simple relation between what is the radius of the RBF and the shape factor. For the Gaussians, and for both the Gaussians and the C4 that are implemented in SPICY, the radius is defined as the distance from the barycenter at which the basis is equal to 0.5. And once we have collocated and placed our basis functions, what we can do is to simply repeat this different times for different values of k's. And by doing that, that's why we have various levels, you will obtain a distribution of placing a collocation of many bases, some which will be large, some other that will be small. The large one to capture, say, large scales in the data, and the small ones to capture the small scale in the data, say strong gradients such as boundary layers or things like that. But here what is important is that by construction, large scale or small scales are indirectly defined based on the number of particles that you have. So if you have very few particles, the smaller you can get is still quite large, right? And somehow you try to ensure that the collocation would be very robust. So to conclude, what SPICY will ask when preparing the clustering is the following. We'll have 4 inputs. First, it will ask the vectors of nks. So these are the ones that will be used to collocate the bases at the different levels. So in this example, I'm giving 3, 6, 50, 200, means that there will be the first level with about 3 particles per basis, then about 6 particles per basis, and so on and so forth. The second input is a new feature, which is the definition of the areas within which these levels will be placed. So in this case we are defining 2 polygonal areas, and I will show you in the tutorial how to do that. and the clusterings with the level of 3 particles per basis and 6 particles per basis will be placed in different polygons, different areas, whereas if you leave this empty, it simply means that this will be placed everywhere within the domain, within all the space, let's say, spanned by the particles. The third input is a vector with two numbers, which defines the minimum and the maximum radius that are going to be tolerated. This is really like a sort of safety measure in case something goes wrong and you can have too big radiuses or too small radiuses. This will act as caps, as clips. Things larger than 0.3 in this case will be capped to 0.3, and bases smaller than 0.15 will be capped to 0.15. And the last is the epsilon parameter, which I told you. So in this case, each basis will have a value of 0.87 at its nearest barycenter, at its nearest colleague, let's say. This might look like a large number, but in fact it's not, and it's a good number. You do want to have the bases to talk to each other, to overlap to each other sufficiently enough, let's say, to ensure a good reconstruction. The last aspect I would like to talk about in the session on numerical methods is about the linear system solvers. I've been working on different numerical techniques, both direct and iterative solvers, and Manuel Ratz will present the recent developments in the last video of the course. These are mostly based on partition of unity methods, PUM, which allows to save a lot of memory requirements. But for the moment in SPICY, this is not implemented. We have instead our good old method, which was developed together with Piero Sperotto and Sandra Pieraccini, and it is based on Cholesky decomposition. It is much heavier than the PUM, but the solver is very robust. So I want to go with you through the ideas of this because the inputs that you will have to provide to SPICY somehow are related to the way it will solve the system. So let's take back the linear system which we have been playing with throughout the whole course. You remember we are solving for the weights W and the Lagrange multipliers lambda. And the first thing which I encourage you to do is to extract the weights from the first equation. So you will obtain this equation here, and then insert this result into the second one, and what you will obtain is a linear system for the Lagrange multipliers. Now what you should notice here is that you have the matrix A inverse appearing two times, and both of the times it's multiplied on the left by B transpose. So there's a nice way to avoid computing this product twice, and that is to solve, if you want, a set of adjoint problems, in particular solving n lambda systems. What I'm talking about is solving this problem for the n. You will just multiply on the left by the inverse of A if you wish, and what you obtain is that n transpose is in fact precisely what we are looking for here, those two terms. We can solve this once and then use this solution directly to compute both m's on the left hand side, and to compute the B2 star on the right hand side. This lets you save a lot of a lot of operations. But what is even more interesting is that if you solve this in a clever way, then you can also reuse some of this computation later to compute the weights. And now what's the clever way here is to use Cholesky factorization. That will break the matrix A into two triangular factors, and then you can use triangular system solvers to replace A inverse everywhere, and this will be very efficient. However, for this to work, you need to have a positive definite, and this is not ensured by our collocation method, and so this means that we have somehow to enforce it, and this is where the alpha 1, the Tikhonov of regularization I've been talking about in the previous videos, become very, very important, and that alpha 1 plays a big role. Now, it's not easy to find the right alpha 1, the right amount of regularization. The principle which we follow here is to try to put the least that you need to ensure that the matrix A is symmetric positive definite, so that everything else can go easily, but at the same time without modifying too much the system with respect to the original version. And so here is the complete algorithm. The first step will be to compute this alpha 1, and we will do that using as an information the largest eigenvalue of the matrix A and an input of the user, which is this K, which plays somehow a proxy of the condition number. Now you can show that there is a simple relation between the condition number that you desire in a matrix and the amount of Tikhonov regularization that you have to add. And you can easily show that this relation is the following, and it will involve the desired condition number, the smallest eigenvalue of A, and the largest eigenvalue of A. Computing the largest eigenvalue of A is not very expensive, but computing the smallest eigenvalue of A is very expensive and also very imprecise. So what we did here was to simplify this relation. So K usually is a very large number, you can easily forget about this one, but this product is not necessarily something you can forget about, because K is very large, lambda is very small, the product might not be so small, but as I said, computing the smallest eigenvalue it can be tricky, so we will neglect this. And what we have is this relation where K is, let's say, an approximation of the condition number, and you can show that this is quite a conservative estimate, so it will give you a slightly larger alpha than what you need, which it's still okay. Now once you have the alpha, you can regularize the matrix A, and then you can compute the Cholesky factors. And once you have the Cholesky factors, you can use them to solve the adjoint systems that we have seen before using triangular system solvers. This goes very fast. Once you have this, you can compute the terms that I was talking about before, so beta transpose A minus 1, and then with this you can assemble the linear system for the constraints. This is hopefully also a symmetric positive definite matrix M, so we can again use Cholesky factorization to solve for the lambdas. And once we solve for the lambdas, we can finally go back to solving for the W's. We have the lambdas here, and we have the Cholesky factors that lets us solve this again using triangular system solvers, and this goes very fast. Now this is the call of the solver. We will go into more details in the tutorials, but it suffices to notice that usually you have only just one input, one parameter, which is this K count. This K count here is basically this K, which I talked about before, and here, as you can see, we're putting a large number K, 1 to the 12, 1e to the 12. That's it. This is everything I had to tell you about the theory of SPICY. So now you know everything about the theory behind constrained radial basis functions, how to use it for regression, for PD integration. And in this last video we covered the last two pieces of the puzzle, which were the collocation and the shape of the radial basis functions, and the numerical techniques to solve the problems. That's enough for this video. I look forward to see you in the next videos, which from now on are going to be under the tutorial exercises of the SPICY class. See you there.